All right, AP Stats students. Today we're going to be looking at section 2.2, density curves and normal distributions. Can't stress how fundamental what we're about to do is. We're really starting to turn a curve, no pun intended. All right, so after this section, we should be able to estimate the relative locations of the mean and median on a density curve. We should be able to estimate areas or proportions of values in a normal distribution. We should be able to find the proportion of z values on a specified interval or a z-score from a percentile in the standard normal distribution. We should be able to find the proportion of values in a specified interval or the value that corresponds to a given percentile in any normal distribution. And we should be able to determine whether a distribution of data is approximately normal from graphical and numerical evidence. Okay, so those are our goals, learning objectives for this section. All right, so in Chapter 1, we developed a kit of graphical and numerical tools for describing distributions. Now we're going to add one more step to the strategy. So exploring quantitative data. We always want to plot your data, make a graph, usually a dot plot, stem plot, or histogram. We want to look for an overall pattern, shape, center, and spread, and for striking departures such as outliers. And you want to calculate a numerical summary to briefly describe the center and spread. But we're going to now add that sometimes the overall pattern of a large number of observations is so regular that we can describe it by a smooth curve. And that's where we're going to run into a density curve. A density curve is a curve that is always on or above the horizontal axis, and it has an area exactly 1 underneath it. Now, I just want to pause for a minute because I'm looking at my former AP Calculus students, the students that have taken calculus already and now are in stats, and I'm watching you freak out. Yes, I just said the area under the curve is 1. And yes, there are totally connections here. But no, we are not going to exploit them. So, anyways, for the rest of you, you're totally lost about what I was just saying. Overlook me. Ignore that part. Moving on. A density curve describes the overall pattern of a distribution. And the area under the curve and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval. For example, the overall pattern of the histogram of scores of all the 947 7th grade students in Gary, Indiana, on the vocabulary part of the Iowa test of basic skills can be described by a smooth curve drawn through the tops of the bars. So this is some sort of standardized test somewhere. Not really sure all the context of it, but anyways, it's standardized test scores here, and you can see that it can be described by that smooth curve that they've drawn over the bars there. And it's not perfect by no means, as you can see, but that is an estimate for this distribution, is that curve. All right, our measures of center and spread apply to density curves as well as to actual sets of observations. The median of the density curve is the equal areas point. Basically, it's the point that's going to divide the area under that curve in half. Okay, wherever that is, it's a point that when I take a line and down from that point along that curve down to the x-axis, I get an equal area on either side. Okay. The mean of it, though, is the balance point. That's the point at which the curve would balance if made of solid material. So if I had that curve, it was made of solid material, that's the balancing point for that. The mean and the median are the same for a symmetric density curve. They both lie at the center of the curve. The mean of a skewed curve is pulled away from the median in the direction of the long tail. Okay, and we've already talked about that, really. And I've hinted on to curves already. A little bit. I really kind of hinted on to density curves. We've been kind of building up to this for a little bit now. So that's already something we've kind of talked about. So here's the mean. Here's two curves. This one's the first curve over here on the left is very the first curve is very symmetric here. So this curve right here is pretty symmetric. The mean and the median are going to be about at the same spot right there. Now we've got a curve that's right skewed. The right tail is a little bit longer, so the mean is going to be pulled to the right, whereas the median is still at that point that's going to divide that area in half. Okay, the median is a little more resistance to outliers. A density curve is an idealized description of the distribution of data. We distinguish the mean and standard deviation of the density curve and the mean and standard deviation computed from the actual observations. The usual notation for the mean of a density curve is mu. That's the Greek letter mu. And we write the standard deviation of a density curve as the lowercase Greek letter sigma. You've already seen big sigma. It looks like the big E. You sum up that big sigma. This is little sigma. Little sigma, the little lowercase Greek letter sigma. So mu is the mean of the density curve, and sigma is the standard deviation of the density curve. We actually will later on learn about those also in another context too. So, all right. Normal distributions. One particularly important class of density curves are the normal curves, which describe normal distributions. Okay, they describe normal distributions. All normal curves have the same shape. They're symmetric, single-peaked, and bell-shaped. Any specific normal curve is completely described by giving its mean mu and its standard deviation sigma. Okay. They're symmetric. Notice both of these curves here are symmetric. They're also bell-shaped. Now, they're a little bit different. Obviously, the one on the right has a taller peak than the one on the left. They also have to have a single peak, not two peaks. Okay, one peak. All right, a normal distribution is described by a normal density curve. Any particular normal distribution is completely specified by two numbers. Its mean mu and its standard deviation sigma. And the mean of a normal distribution is the center of the symmetric normal curve. The standard deviation is the distance from the center to the change of curvature points on either side. And we abbreviate normal distribution with the mean mu and standard deviation as capital N parentheses mu comma sigma close parentheses. So when you see that capital N number comma another number, that means you're given the mean and the standard deviation right there of that normal distribution. It's a normal distribution with that mean and that standard deviation. All right. Why are normal distributions important in statistics? Normal distributions are good descriptions for some distributions of real data. They're also good approximations of the results of many kinds of chance outcomes. And many statistical inference procedures are based on normal distributions. There's lots of things in the real world that are distributed normally. They have a normal distribution, so that they're hugely important. This type of distribution. There's other types of distributions that we will learn about here in statistics, but there are none that will ever really rise up to the level of importance as normal distributions. Nonetheless, there's others are still important, but a normal distribution is critically important. All right. The 68, 95, 99.7 rule. Surely you've heard of that rule before. Although there are many normal curves, they all have properties in common. The 68, 95, 99.7 rule basically says in a normal distribution with mean mu and standard deviation sigma, 68% of the data is going to fall within one standard deviation or sigma of mu, the mean. 68% of the observations will fall within one standard deviation of the mean. So from the mean, you take one standard deviation to the right, one standard deviation to the left. 68% of those are going to fall under there. Remember, the area under these density curves is 1. So the area under this portion of the graph would be 0.68. Okay, because the whole area under the curve is 1 or 100%. 100% of the data. 95% are going to fall within 2 sigma of mu, or 2 standard deviations of the mean. So you go 2 standard deviations out to the left, 2 standard deviations out to the right. That range of values, 95% of the data is going to fall into that range. And 99.7 will fall within 3 standard deviations of the mean, or 3 sigma of mu. All right. The standard normal distribution. All normal distributions are the same if we measure in units of size sigma and the mean mu is center. The standard normal distribution is the normal distribution with mean 0 and standard deviation 1. If a variable x has any normal distribution with mean mu and standard deviation sigma, then the standardized variable z equals x minus mu divided by sigma. We've seen that before. That looks like x minus the mean divided by the standard deviation. That looks like a z-score. It is. This value, this z variable, has the standard normal distribution, meaning that it has a mean of 0 and a standard deviation of 1. All right. In AP Stats, they love to use tables. And I'm going to tell you all right now, you're given, if you take the AP Statistics exam, you'll be given tables to be able to calculate area under density curves. However, there's functions on the calculator that will also do the same thing. And I know as soon as I show you the functions on the calculator, you are not going to depend on the tables. I really don't even like teaching the tables, honestly, and I'm not going to. On the AP test, they don't necessarily expect you to use the tables. They provide you with the tables if you want to use the tables. What you do have to do is draw a picture, and you'll see what I mean when we look at an example. But anyway, suppose we want to find the proportion of observations from a standard normal distribution that are less than 0.81. We can use this table, and they'll show you how to do that. Okay, I'm going to skip through that, though, because I want to go on a little bit further. We can answer a question about areas in any normal distribution by standardizing them and using that table. So you can standardize it. You also can technically not have to standardize it. There's a function on the calculator. We can perform the calculation, show the work. You can either do that, compute the z-score for each boundary value, and use table A to technology to find the desired area under the standard normal curve, or what you're probably going to do is use the normal CDF command and label each of the inputs. And then finally you answer the question. So first you state the distribution. So you draw a normal curve. First thing you want to do is draw your normal curve with the area of interest shaded. The mean and the standard deviation, the boundary of the value clearly identified. Then you perform the calculations. Most likely, I know you're going to probably use the calculator, label each of the inputs, and then you're finally going to answer the question at the end. So, for instance, with this example right here, the mean is 0, the standard deviation is 1, and we want the probability that z is less than 0.81. So, the way we're going to do that on the calculator, I'm going to show you all real quick, but I'm going to make sure that I've got this right. That's really weird. All right, this is really weird. I'm not kidding. This calculator right here, I literally had the right numbers and everything in it. That's super strange. It's like I didn't do this since the last time that I used it. Anyways, let me show you on the other calculator real quick. Okay, let me show you on this calculator real quick. Hopefully you can see this. All right, so we can actually, on the calculator right now, we could calculate that. So what we're going to do is we're going to hit second vars. Remember I told you the distribution menu, you're going to find things in here that we need to use. And you see there's a normal CDF right there, number 2. Okay, there's other functions down through here, but we're looking for normal CDF. It's number 2. Now, immediately your calculator is going to look totally different than mine because, and I actually prefer the way yours looks. Your calculator is going to ask for a lower, an upper, mu, and then sigma. The lower value, if we want the z-score to be less than 0.81, We don't care how far down it goes. So we're going to trick the calculator. We can't literally type negative infinity in, but we can type something that's so big in the negative direction that it's basically negative infinity. And the value that you're going to use is -1. Whoops. Sorry. Hold on a minute. I used the wrong button. So number 2, -1. Make sure you use the negative button, not the subtraction button like I just tried. -1, and then you're going to hit second. It's the comma button right here. That's how you access the big E, which is basically time. That's scientific notation. That means times 10 to whatever power you're fixing to type in here. And we're going to type in 99. Okay, so that's -1 times 10 to the 99th power. That's a really big number in the negative direction. Okay, it's really big in the negative direction. If that's not really a proper way of saying that, that's a very that's a negative number with a large absolute value. There we go. Want to be proper about that. So that's what you're going to put in for your lower value. Okay, your lower value. Okay, again, I can't do that because my calculator looks a little bit different than yours. But that's what you're going to type in there for your lower bound. For your upper bound, you're going to type in 0.81 because that's what I want Z to be less than, 0.81. So I want everything up to 0.81. So I'm going to type in 0.81. Now, if we had wanted to do something like Z is greater than something, our lower bound would be whatever we want it to be greater than, and our upper bound would be +1 E99. Okay, that basically, -1 E99 is like negative infinity, and +1 E99 is almost like positive infinity. As far as the calculator running calculations, that's basically true. Then you're going to type in the mean, which is 0, and the standard deviation, which is 1. And finally, you'll close parentheses. Or for you, you don't close parentheses. You hit paste, and then you hit enter. And when you do that, you get the answer, 0.7910. Was that not the answer they had right here? Yes, it is. That's how you can use the normal CDF function. Whoops. Okay. That's how you can get that area. But you need to draw the graph, draw where about 0.81 is, and shade the area to the left of that because you're wanting Z's less than 0.81. Shade that area to the left of that. That's going to allow you to show that you know what you're talking about. Then you can show that you did a normal CDF if you want to. They really don't like it if you they don't like calculator jargon. They don't like for you to type in the syntax of the calculator or whatever. So honestly, it's not even really necessary that you do the normal CDF, but you have to show that you've got that area there and that you're doing this by computing the normal CDF. You're using the normal CDF command, but you got to show that you know what you're talking about with drawing that. Then answer the question. So, if we went back to that question, it asked for that probability there, the values of the distribution that are less than 0.81. What proportion? You'd say the proportion of observations from this distribution that are less than 0.81 is 0.7910. Period. Answer. All right. Moving on. We can also work backwards with normal distribution. We can find this is how we can find values from areas in a normal distribution. So sometimes we just want to find the observed value that corresponds to a given percentile. Again, there's 3 steps. We can state the distribution and draw values of interest. You're going to draw the normal curve, the area of interest shaded, and the mean and standard deviation and unknown boundary value clearly identified. And then you can perform calculations. You can do one of the following. You use a table, which you're probably not going to do. Or you can use the inverse norm command, which if you remember in the distribution menu, that was right below normal CDF. That was number 3. That's the inverse normal command to answer the question. Okay, that would allow us to find a value at a a certain percentile. Okay. By the way, we can change the mean and the standard deviation to be the mean and the standard deviation of whatever normal distribution. The standard normal distribution has a mean of 0 and a standard deviation of 1, but that doesn't mean that all normal distributions have that. It may be a normal distribution with a mean of 17 and a standard deviation of 5. Okay, then you still use the normal CDF to calculate the area under the curve. In inverse norm, when you do that one on the calculator, it's going to ask for the area. So that's the percentile. If you want the 80th percentile, let's say that the mean is a 55 and the standard deviation is a 11. You can find out what that the 80th percentile would be. It would be a 64 in that case. So you can figure out what score it would take to get it the 80th percentile in that distribution, perhaps. So that's kind of working backwards. That's finding the value given the area. Whereas before we were given the value, but we wanted to find the area. So it's kind of backwards of what we just got done doing. Normal distributions provide good models for some distributions of real data. Lots of procedures later on. So we already talked about that. A normal probability plot gives a good assessment of whether the data set follows a normal distribution. If the points on a normal probability plot lie close to a straight line, then the plot indicates that the data are normal. Systematic deviations from a straight line indicate a non-normal distribution. Outliers appear as points that are far away from the overall pattern of the plot. Okay, there was our learning objectives for this lesson.